Dear students, I welcome you all for our lecture series on food technology. In today's lecture, let's make an attempt to know about carbohydrates. This is the second part of the lecture series on carbohydrates. We have learnt that carbohydrates are an important source of energy for animals and are found as natural food components and as added ingredients in the food. The reactive nature of carbohydrates to both chemical and biochemical modification makes them as one of the widely used products in commercial food processing. Carbohydrates can lead to improvement in the properties of the food on modification and owing to their reactivity to various chemicals, thus extending their use in many products. The monosaccharides have the ability to react with acids, alkali, amino acids and also on heating to form various derivatives that can improve flavor and color of a food substance. Maillard reaction and caramelization are important reactions of carbohydrates, especially monosaccharides, which are practically used in the preparation of a wide variety of processed foods. Starch is an important polysaccharide of interest in terms of application in food processing. The intermediate products and end products of starch have wide applications. The following aspects will be covered under part 2. 1. Chemical reaction of carbohydrates. 2. Hydrolysis of starch. 3. Modified starches and their applications. And 4. Modified cellulose and its applications. Now let's start the first topic, chemical reactions of carbohydrates. All carbohydrate molecules have hydroxyl groups available for chemical reaction. Simple monosaccharides and most other low molecular weight carbohydrate molecules also have carbonyl groups available for reaction. The individual type of reactions is dealt one by one as follows. The first one being oxidation, leading to the formation of aldonic, uronic and dicarboxylic acids. Aldoses are oxidized to aldonic acids under mild conditions, for instance with bromine water in a buffered neutral or alkaline media. Beta pyranose is oxidized more rapidly than the alpha form. Felling's solution is an alkaline solution of copper that oxidizes an aldose to an aldonate and in the process get reduced to copper with one positive charge, which precipitates into a brick red colored cupric oxide. The acid name is obtained by adding the suffix onic acid. For example, aldose will become aldonic acid. A simple and specific method for quantitative oxidation of D-glucose to D-gluconic acid uses the enzyme glucose oxidase, the initial product being the 1,5-lactone, which is an intramolecular ester of the acid. The conversion of D-glucose to D-gluconic acid is shown in figure number 1 on the screen. If you look at the figure, in the D-glucose structure, there is a change in the C1 carbon atom where the aldehyde group will be converted to carboxylic group and later termed as D-gluconic acid, which is an aldonic acid. Oxidation of the hydroxymethyl group or CH2OH group by retaining the carbonyl function at carbon 1 molecule leads to the formation of uronic acids. Depending on their configuration, the uronic acids can form lactone rings in pyranose or furanose forms. The structure of D-galacturonic acid is shown in figure number 2 on your screen. So, if you have a look at the figure, D-galactose, that is C5, which is a hydroxymethyl group, will be converted to carboxylic group and later termed as D-galacturonic acid. Treatment of aldose with more vigorous oxidizing agents such as nitric acid brings about oxidation of the C1 aldehyde group and the hydroxymethyl group, resulting in the formation of a dicarboxylic acid. An example is D-glucuric acid as shown in the figure number 3 on your screen. In the figure, at C1 and at C6 there are changes. So at C1, aldehyde group will be converted to carboxylic group, and at C6 the hydroxymethyl group will be converted to carboxylic group again. Finally, the end product will be termed as D-glucuric acid. The next reaction of interest is reduction to the formation of sugar alcohols. Hydrogenation is the addition of hydrogen to a double bond. When applied to carbohydrates, it entails addition of hydrogen to the double bond between the oxygen atom and the carbon atom of the carbonyl group of an aldose or ketose. The alcohol name is derived from the sugar name in each case by replacing the suffix OSE or ULOSE with the suffix ITOL or etol. The hydrogenation of D-glucose leads to the formation of D-glucitol, commonly known as sorbitol, as shown in the figure number 4 on your screen. In the figure, at C1, after addition of 2 hydrogen atoms, the aldehyde group will be converted to a carboxymethyl group, which is commonly termed as sorbitol. Sorbitol is widely distributed in plants and is used as a general humectant as well as a sweetener. D-mannitol can be obtained by the hydrogenation of D-mannose. It has been used as a non-sticky coating on candies. It is 65% as sweet as sucrose and is used in sugar-free chocolates. Xylitol is produced from hydrogenation of D-xylose obtained from hemicelluloses from trees. They are used as sugar substitutes in dietetic food formulations and as softeners in dehydrated foods. The next important reaction of carbohydrates is formation of esters. The hydroxyl groups of carbohydrates form esters with organic and some inorganic acids. Reaction of hydroxyl groups with an activated form of a carboxylic acid in the presence of a suitable base produces an ester. Esters are chemical compounds derived from an acid in which at least one hydroxyl group, that is OH, is replaced by an alkyl group, that is O. Carbohydrates occur in nature as esters of acetates, succinates and carboxylic acid. They are especially found as components of polysaccharides such as potato and cornstarch. The formation of glucose 1-phosphate from glucose is shown in figure number 5 on your screen. If you take a look at the structure of glucose, the hydroxyl group at the 5th carbon atom is replaced by an alkyl group in connection with the C1 carbon atom, leading to the formation of alpha D-glucose 1-phosphate. The next important reaction is formation of ethers. The hydroxyl groups of carbohydrates have the ability to form ethers as well. Ethers are classes of organic compounds that contain an ether group, that is an oxygen atom connected by 2 alkyl groups. Ethers of carbohydrates are less prevalent in the nature. Commercially, polysaccharides are etherified with an intention to modify their properties and to make them more useful. Examples are the production of methyl, sodium carboxymethyl and hydroxypropyl ethers of cellulose and hydroxypropyl ethers of starch. These derivatives are used in food industry. The next reaction is caramelization. Heating of carbohydrates, especially the disaccharide sucrose and other reducing sugars, without nitrogen containing compounds result in a series of reactions known as caramelization. This reaction is facilitated by small amounts of acids and certain salts. This process is similar to non-enzymatic browning but does not involve amino acids. The final product is termed as caramel, which contains a complex mixture of polymeric compounds which are made up of unsaturated cyclic compounds, which can be 5 and 6 membered rings. The caramelization of sucrose is shown in figure number 6 on your screen. Compounds with flavor and aroma are also obtained. Heating causes dehydration of the sugar molecule, followed by introduction of double bonds or formation of anhydro rings. These unsaturated rings further condense to form conjugated double bond containing polymers with brown color. Caramel is also produced commercially by heating a carbohydrate alone in the presence of an acid, alkali or salt. D-glucose, invert sugar, glucose syrups and malt syrups are also used apart from sucrose to produce caramels. Food grade acids are used, namely food grade sulfuric, phosphoric, acetic and citric acids. Bases which can be used are ammonium, sodium, potassium and calcium hydroxides. Salts that may be used are ammonium, sodium and potassium carbonates, bicarbonates, phosphates, etc. The next important reaction is reaction with amino compounds or Maillard reaction. The browning of foods commonly seen on heating or on storage of foods is due to a chemical reaction between reducing sugars, mainly D-glucose, and a primary amino group, that is a free amino acid or amino group on a side chain of a protein molecule. This reaction is called the Maillard reaction and the overall process is termed as Maillard browning. This reaction does not involve the role of enzymes, thus is also known as non-enzymatic browning. Enzymatic browning can be seen in freshly cut fruits and vegetables. The end products include soluble and insoluble polymers. The main sugars which react are mainly glucose, fructose, maltose, lactose and to a smaller extent ribose. The volatile compounds produced by the Maillard reaction during baking, frying or roasting often produce desirable aromas. The end products are also important contributors to the flavor of milk chocolate, caramels and toffees, during which reducing sugars react with milk proteins. The Maillard reaction also produces flavors with bitter substances that may be desired in foods like coffee. The Maillard reaction can also result in off flavors and off aromas which are most likely to be produced during pasteurization, storage of dehydrated foods and grilling of meat or fish. The three stages occurring in the Maillard reaction are condensation of a reducing sugar and amino acid group leading to the formation of N-glycosylamine in case of aldoses, which rearrange to form Amadori product. The second step is the fragmentation of the complex Amadori product. The last step involves dehydration, fragmentation and polymerization leading to the formation of end products with flavor. And the next important reaction is formation of acrylamide. The Maillard reaction is also responsible for the formation of acrylamide in many foods that have been heated to a high temperature during processing or preparation. Acrylamide is a known neurotoxicant and a weak carcinogen in humans. Acrylamide is derived primarily from the reaction between reducing sugars and the alpha amino group of free L-aspargine, an amino acid. Foods with free L-aspargine and reducing sugars are susceptible to the formation of acrylamides on heating to a high temperature, such as fried potato products, which includes chips and French fries. And the next important topic is hydrolysis of starch. Starch molecules undergo depolymerization by hot acids similar to other polysaccharide molecules. Hydrolysis of the glycosidic linkage occurs initially to produce very large fragments. Acid modified starches form gels with improved clarity and increased strength, and they provide less viscosity when solutions are formed. More extensive depolymerization of granular starch with acid produces dextrins. Dextrins produce lower viscosities in solutions and can be used at high concentration in food processing. Incomplete hydrolysis of cooked starch dispersions with either an acid or an enzyme produces mixtures of malto-oligosaccharides, which are industrially referred to as maltodextrins. Maltodextrins are usually described by their dextrose equivalency, or in short DE. Dextrose equivalency is a measure of the amount of reducing sugars present in a sugar product relative to dextrose. DE is expressed as a percentage on a dry basis. For example, a maltodextrin with a DE of 10 would have 10% of the reducing power of dextrose, which has a DE of 100. Dextrose equivalency is inversely related to average molecular weight. Maltodextrins of lowest DE, that is highest average molecular weight, are non-hygroscopic, while those of highest DE tend to absorb moisture. If hydrolysis is continued, starch produces a mixture of D-glucose, maltose and other malto-oligosaccharides. They are used in concentrations of high osmolality, that is about 70% solids, which is high enough to avoid growth of microbes. Various enzymes are also used in the hydrolysis of starch into D-glucose. Alpha amylase is an enzyme that cleaves both amylose and amylopectin molecules, producing oligosaccharides. Glucoamylase or amyloglucosidase is another enzyme used commercially in combination with alpha amylase for the production of D-glucose, syrups and crystalline D-glucose. There are several other debranching enzymes that specifically catalyze the hydrolysis of 1,6 linkages in amylopectin, namely isoamylase and pullulinase. For the production of D-fructose, a D-glucose solution is passed through a column containing glucose isomerase enzyme, leading to the formation of end product with higher fructose content. The overall scheme of starch hydrolysis is presented in figure number 7 on your screen. So, initially Starch on hydrolysis yields dextrins. Dextrins on hydrolysis yields maltose, and maltose on further hydrolysis will liberate glucose. The next important topic is modified starches and their applications. Starch properties can be modified by physical and chemical methods. Such modifications are done by the food processors as they require starches with better physicochemical properties than that of native starch or starch in their natural form. When cooked, the native starches are known to produce a rubbery paste which form gels with undesirable consistency when the pastes are cooled. Thus, modification is done with an aim to improve the characteristics of the pastes and gels. The specific targets of these modifications will be to improve the ability to withstand the conditions of heat, shear and acid associated with particular processing conditions and some specific functional properties. Modified food starches are functional, useful and are abundantly used as food ingredients and additives. Chemical modification of starch leads to the formation of cross-linked, stabilized, oxidized and depolymerized, that is acid modified, thin boiling products. Physical modifications lead to the formation of pre-gelatinized and cold water swelling products. The overview of starch modification is shown in figure number 8 on your screen. If you look at the figure, there are two techniques of starch modification, one chemical and two physical. Chemical degradation can lead to the formation of acid or oxidation or formation of dextrins. The other two sub-techniques are esterification and etherification, and cross-linking results in esterification of starch. And the next type of modification is physical, where the starch is subjected to pre-gelatinization and further will be processed using a roll drying or spray drying or thermal drying. The next topic is stabilized starches. The starch products that are esterified or etherified with monofunctional reagents resist the interchain associations. This phenomenon reduces the tendency of the starch paste to form a gel and also the tendency for precipitation to occur. Hence, this modification is often called stabilization and the products are called stabilized starches. Stabilized products have lower gelatinization and pasting temperatures and they are easier to redisperse when pre-gelatinized. They also produce pastes and gels with a reduced tendency for retrogradation. Now, retrogradation is a realignment of amylose and amylopectin chains after gelatinization. In other terms, the end products have a greater stability, improved freeze-thaw stability and greater clarity as compared to the untreated starch. Hydroxypropylation is the most often used reaction to prepare a stabilized starch product. Hydroxypropyl starches prepared by reacting starch with propylene oxide to produce a low level of etherification. They are used as thickeners and extenders in food products. The next type of starch is cross-linked starch. Cross-linking in the starch granules occur when the granules are made to react with bifunctional reagents that react with the hydroxyl groups on two different molecules within the same starch granule. Cross-linked starches are obtained by the reaction of starch with bi or polyfunctional reagents such as sodium trimetaphosphate, phosphorus oxychloride, epichlorohydrin or mixed anhydrides of acetic and dicarboxylic acids. The starch granule thus treated will have increase in the gelatinization temperature and lowered swelling power. Starch stability remains high at extreme pH values. Cross-linked starch derivatives are generally used when high starch stability is demanded. Cross-linked starches have increased resistance to shear and increased stability to low pH conditions, and they can produce paste with greater viscosities and stability as compared to the native form of starch. The next starch products are oxidized starches. Starch hydrolysis and oxidation occur when aqueous starch suspensions are treated with sodium hypochlorite at a temperature below the starch gelatinization temperature range. The products obtained have an average of 1 carboxyl group per 25 to 50 glucose residues. Oxidized starch is used as low viscosity filler for salad dressings and mayonnaise. Oxidized starch does not retrograde nor form an opaque gel. The next type of starch hydrolysis products are thin boiling starches. Partial acidic hydrolysis of starch yields a product which is readily soluble in boiling water but not in cold water. The solution has a lower viscosity than the untreated starch and remains as a fluid after cooling. These starches are utilized as thickeners and as protective films. The next type of starch hydrolysis product is cold water swelling starch. Granular starch that swells extensively in cold water is made by heating cornstarch in 75 to 90% ethanol or by spray drying process. The granules will remain intact, thus when added to water they can swell as if they are being cooked. The dispersion made by incorporating cold water swelling starch into sugar solutions or glucose syrups by rapid stirring can be poured into molds which can further set to form a rigid gel. This gel can be sliced and is used in making desserts and muffins. The next type of starch hydrolysis product is pre-gelatinized starch. Heating of starch suspensions followed by drying results in the formation of end products that have the ability to swell in cold water and can form gels on heating. The granules in the end product will be destroyed because of the heating. The advantage of pre-gelatinized starches is that they can be used without cooking. They are used in dry mixes such as instant pudding mixes. And the next topic of importance is modified cellulose and its applications. Cellulose can be modified into a number of derivatives with good swelling properties and improved solubility. Such derivatives have a wide field of application in food industry. One such product is carboxymethyl cellulose. Carboxymethyl cellulose is widely used as a food gum. Treatment of purified wood pulp with 18% sodium hydroxide solution produces alkaline cellulose. Carboxymethyl cellulose is obtained by treating this alkaline cellulose with chloroacetic acid. Carboxymethyl cellulose is an inert binding and thickening agent used to adjust or to improve the texture of many food products such as jellies, paste fillings, cheeses, salad dressings, cake fillings and icings. The next product is methyl cellulose and hydroxypropyl methyl cellulose. The reaction of cellulose with methyl cellulose or propylene oxide in the presence of a strong alkali introduces methyl or hydroxypropyl groups into cellulose molecules. Depending on the nature of the substituent, which can be a methyl, ethyl, hydroxymethyl, hydroxyethyl or hydroxypropyl, and the degree of substitution, products are obtained with various swelling capacity and solubilities. The presence of methyl and methyl hydroxypropyl celluloses in baked products obtained from rice, wheat or corn decreases the crumbliness of the product and enables a larger volume of water to be added into the dough. This improves the extent of starch swelling during oven baking. They are also used to reduce the amount of fat in food products because they can provide fat-like properties to the food product, leading to the reduction in fat addition, and they also reduce adsorption of fat in products subjected to frying. Thus, we can conclude that the structure of many carbohydrates appears to be complex, but the chemistry of these substances involves only two functional groups, the ketone or aldehyde carbonyls and alcohol hydroxyl groups. The intermediates and derivatives they form are dependent on the many aspects such as substituent used, chemicals used, temperature applied and enzymes used. Many of these derivatives have important food applications which lead to improvement in functional and sensory properties of foods. Thank you.